My name is Peter. I'm from the UK. I work as a freelance Python programmer. I quite often spend time, just sort of short periods of time with companies. And the genesis of this talk was earlier in the year. I was doing some work for a company, and the company had got a system that had been written by some contractors who'd then left, and they left this big mess, and nobody really knew how it worked and what to do with it, and it had lots of bugs in it, and we had to think about how we were going to fix these bugs. But it struck me fairly early on that we didn't do much thinking about how we were thinking about fixing bugs, and that's what I'm going to be talking about today. I'm going to be talking about how we solve problems in general, and in particular how we solve problems when we are debugging code. So really this is a talk about thinking about thinking. This is my only slide. This is not a technical talk, so unlike yesterday there will be no code. I'm going to talk for a while, and then at the end I'd like to have a bit of a discussion about some of the ideas that I've talked about and some of your own experiences. So this is George Pólya. George Pólya was a Hungarian mathematician who lived and worked in the middle part of the last century, and I'll be talking more about him as we go on. But I'm going to begin by talking about Richard Feynman. So you may have heard of Feynman. He was also active in the middle part of the last century. He was I guess a particle physicist, really. He did early work on the Manhattan Project, which was the Americans' project to develop nuclear weapons during the Second World War. He was the first person to come up with the ideas about quantum computing, and he was also a great teacher. During the later parts of his life, he wrote some books called the Feynman Lectures, and he had this idea that if you've got a complex idea and you can't explain it to a first-year undergraduate, then you don't understand it well enough yourself. So he had this reputation as being a great explainer, but he was also frighteningly intelligent. And in an interview, I think, after his death with Murray Gell-Mann, a reporter from the New York Times, I think, asked him how Feynman went about solving problems. And Gell-Mann said, well, Feynman has this algorithm. Step 1, write down the problem. Step 2, think really hard. Step 3, write down the solution. Now, if you've got a brain the size of a planet, like Feynman obviously did, then this perhaps makes sense. And I think it's probably unfair that Feynman's become associated with this algorithm, given his work as an educator. But his algorithm, whether he came up with it or not, is fantastically unhelpful to us, because it sort of perpetuates a myth that if you're smart, you can just solve problems without a method, perhaps. But Feynman clearly did have a method, but it just wasn't captured in this algorithm. And that brings me on to George Pólya. As I said, Pólya was a Hungarian. He worked in universities across Europe in the 20s and 30s, and then in 1940 left Europe pretty much for good, and ended up teaching at Stanford in California. I don't know whether Pólya and Feynman ever met, but I like to think perhaps they did, and talked about how they encouraged their students to learn. Pólya's field was number theory and combinatorics and probability, and he wrote some sort of interesting papers on that, but he's known best for a book called How to Solve It, which I've got here. I studied maths at university, and every lecturer we had said that we really ought to read this book. And it's about how to think about solving mathematical problems, and more than that, it's about how to teach thinking about solving mathematical problems. So just as an example, an example of the kinds of problems that he is approaching in this book. Bob has 10 pockets and 44 silver dollars. He wants to put his dollars into his pockets, so distributed that each pocket contains a different number of dollars. Can he do so? Or Bob, Peter and Paul travel together. Peter and Paul are good hikers. Each walk p miles per hour. Bob has a bad foot and drives a small car which 2 people can ride but not 3. The car covers c miles per hour. The 3 friends adopt the following scheme. They start together. Paul rides in the car with Bob. Peter walks. After a while, Bob drops Paul, who walks on. Bob returns to pick up Peter, and then Bob and Peter ride in the car until they overtake Paul. At this point, they change. Paul rides and Peter walks just as they started, and the whole procedure is repeated as often as necessary. And the question is, how much progress, that is, how many miles does the company make per hour? One more. From the peak of a mountain, you see 2 points, A and B, in the plane. The lines of vision directed to these points include the angle gamma. This inclination of the first line of vision to a horizontal plane is alpha, that of the second line beta. It is known that the points A and B are on the same level, and that the distance between them is c. Express the elevation x of the peak above the common level A and B in terms of the angles alpha, beta, gamma, and the distance c. I'll be asking you for solutions at the end. So what these problems have in common is that the mathematics that they rely on isn't that difficult. So the first one is basic algebra. In fact, the second one is 2, and the third one is some basic 3D geometry. But these problems are dressed up in a way that it's not necessarily obvious what you need to do to solve them. And Pólya found that high school students, when presented with these problems, would often give up, or they'd try things for a bit and then give up, or perhaps they'd work hard and get to the solution in a very inefficient way. So he came up with not a 3-point algorithm, but sort of 4 steps to break down your problem solving into. And he came up with questions to that teachers should ask their students as their students are solving these problems. So the first step is to understand the problem. The second is to make a plan for how you're going to solve the problem. Part 3 is to actually carry out the plan, and part 4 is to check your solution. So during this talk, I'm going to talk about how these 4 steps can be used when we're debugging a problem. But before that, we should take a step back and ask what is debugging and what is a bug. So debugging, I think, is the art of understanding a bug in your code and fixing it. I guess that's fairly straightforward. And I would define a bug to be any bit of behavior of your program that is not what you expect or understand. So examples of bugs might be the bars in the bar chart in this report aren't in order for this kind of report, or it might be on a customer's system, certain requests take twice as long as they ought to, and so we're seeing timeouts. Or it might be when we run the code with this configuration, we get this stack trace, and the program just crashes. So in all these cases, the program is not doing what it should, and it's not doing what we expect, because presumably we or somebody else wrote the program to do a certain job, and it's not doing so. So let's look at these 4 steps of Pólya's sort of process and ask how they affect or impact our sort of debugging process. So step 1 is to understand the problem, and this sounds obvious. I mean, how else are you going to debug a problem if you don't understand it? But I think certainly I'm too keen to just dive in and start sort of coding away and start sort of putting in print statements and start sort of tearing my hair out without first understanding what the problem actually is. So Pólya advises his students to write down a problem in their own words. And I think it's really useful for us too to write down a description of what the problem, the bug we're seeing is. And this is useful because it helps us straighten out our thoughts. It helps us organize our thoughts about a problem. It helps us to see what's important. And often I think it gives our subconscious a chance to sort of get to work on a problem before we actually start tackling it ourselves. I've lost track of the number of times that I've been working on a problem and getting nowhere, and then I've opened up Stack Overflow and I've begun to write out the question, and just before I sort of click submit, the answer comes to me. And I think just this process of explaining a problem to somebody else is really valuable to help us to understand it. This is sometimes called rubber duck debugging, after having a rubber duck on your desk, so you can explain the problem to the duck rather than to a co-worker. I think that's Joel Spolsky's or somebody else's. So, anyway. So there's definitely an overlap between just describing what a bug is and writing a bug report. Now, some of you are working in companies where there's a QA team, and the QA team will submit defect reports. And there'll be some people on that team who you look forward to receiving bug reports from because they're so clearly organized and so well thought through. And there'll be other people who, quite frankly, you dread getting bug reports from because you'll have to spend the next day sort of teaching critical thinking. I think it's really worth sort of studying what makes for a good bug report, reading through ones which you found useful, and working out what it is about these bug reports that you do find of use. Something else that's useful when you're understanding a problem is to look at what we'd call the repro scenario. So what would we have to do to reproduce this problem? And often it begins, you begin with some sort of very general description of steps to take to reproduce a problem. And part of the later work will be to sort of refine these steps and work out exactly what it is that's the cause. But just having a single sort of starting point as a repro scenario is important, if possible. And beyond that, I think it's really useful to have a single failing test case that demonstrates the problem with your code. This isn't always possible. Sometimes bugs are intermittent. Sometimes they're just too complex to be captured in a single test case. But it's a really useful starting place. So, having begun to get an understanding of the problem, stage 2 is to make a plan. Now, I think in our debugging work, this corresponds to exploring and finding the cause of a bug. This is distinct from step 3, which is actually carrying out the plan and fixing the bug. I think Pólya is keen that we slow ourselves down and we only do one thing at once. So when we're making a plan for how we're going to fix the bug, we need to think about what tools we've got at our disposal for understanding the behavior of our program. So the first and I guess most important tool is just having a text editor that we're comfortable using to read code. Some people will use IDEs that have got functions that allow you to jump to where a class was defined. Other people prefer just to use grep. But being able to sort of read your code easily is a really important first step. You can get tools that draw diagrams of your code, and that can be useful, I think, as well, to give you an idea of how your code sort of fits together. The next thing is the humble print statement. So when you've got some code that runs and you want to see what's going on while you run it, you can often just write print and then the name of your variable to find out what value that variable has. This is pretty low tech, but often quite useful. Although it's a fairly ad hoc kind of solution. And perhaps better is to use logging to log more rigorously. And there are excellent tools that allow you to analyze log files and see what's going on. Next, you can write assertions. The assert statement is not used as often in Python as I think it could or should be. And what assert statements allow you to do is to assert that at a certain point in your program's execution, some invariant holds. If it doesn't hold, the program will raise an exception, and it'll tell you that at some point in your code, some data was not as you expected. Some people think that assertions don't belong in production code. I would disagree with that, and perhaps we can talk about that later. Assertions are there to give you sort of early warning that something's wrong, and they tend to mean that if an assertion is hit now, that means that a problem won't be hit later on. I think part of debugging is finding out sort of the earliest point at which your code is not behaving as you expect, and assertions are valuable for that. And on a production system, you're going to end up with poor behavior either way, I guess. And so having assertions in there will help you with debugging that when that does arrive. And the last tool I've got on my list is tests. And I think tests are obviously very important for ensuring that our code is correct and does what we think. But we can use tests to teach us about the behavior of our code. If there's some code that we don't understand how it works, we can use tests to learn more, and having a sort of a good testing infrastructure is important when it comes to debugging. So, having, I guess, talked about some tools we've got at our disposal, we want to use them to understand how the code behaves. We want to look at the unknown behavior. So, what is it about the code that we don't understand? We also want to use these tools to look at the knowns. So what do we understand? How can we draw parallels between cases that do work and cases that don't? With a repro scenario, what is it about this scenario that causes the bug? Can we make changes that will mean that the bug doesn't manifest itself? What can we learn from comparing these two? I think one of the most important things when debugging is to think about your program execution as being a sort of a linear thing. So although not all programs are not all programs run in a single thread and are deterministic, they all run in time, and there's always a before and an after. So what's the latest point before a bug that we know that code behaves as it should? This is something that assertions are useful for. What's the earliest point after a bug? No, I've got that the wrong way around. What's the latest point we know that the code's behaving well, and what's the earliest point we can find out that it's not? So it's useful to be able to work backwards from where we first see a bug to where the first cause of that bug actually is. I guess we're sort of doing science when we're debugging, so we're forming hypotheses about the behavior of code, and then we want to conduct experiments which either sort of lend weight to these hypotheses or that rule them out. Often in this step, while we're sort of trying to understand the cause of a bug, we realize that we don't actually understand the problem itself. And so we might want to go back to stage one. But if we do think that we've got a good solution to the problem, the next thing to do is to carry out the plan. Now, carrying out the plan probably is the step that is most different between our debugging work and solving the kinds of problems that Pólya had in mind. But some of his advice, nonetheless, is useful. So again, he advises us to proceed slowly and to sort of check each step as we go. Now, sometimes bugs might be easy to fix. There might be a one-line or a one-character change to make. Other times it might require re-architecting an entire component or worse. But I think the advice to proceed slowly and to check what we're doing at each step is good advice. And finally, in stage 4, Pólya encourages us to examine the solution. So with a proof, you want to sort of reread your proof to check through each connection in the proof with a calculation. You want to make sure that the result you get does satisfy the original conditions. And then with a bug that we fixed, we want to make sure that the bug is indeed fixed and that the symptoms have gone away. So this might involve sending the fixed code back to the QA team. It might involve rerunning some tests, but we should always have, I think, new tests that prove that the buggy behavior is gone. And then in this stage, I think it's important to think about how we can avoid hitting this kind of problem again. So this is where we really need to understand the cause of the bug. Was it caused by poor coding practices? In which case, can we think about how we would do code review better in future? Was it caused by poor diagnostics? In which case, what can we do to improve our diagnostics? And so on. So related to that, I guess, is asking what would have made it easier to have debugged this problem. What were we missing? What information were we missing when we came to debug this? So those are the 4 steps. There are obviously differences between debugging our kinds of problems and solving the kinds of mathematical problems that Pólya describes in his book. I guess the difference is sort of between going rock climbing inside, where somebody has laid out a route with the exact handholds and footholds that you need to use to climb the route, and rock climbing outside, where you've just got sort of nature's work to work with. One question that Pólya sort of comes back to is, did you use all the data? And his point here is that in a mathematical problem, the person who's set the problem will have given you just enough information to solve it. And quite often there's some sort of hidden information in the formulation of the problem that isn't obvious at first sight. And although that doesn't directly apply here, I think it's useful to keep asking ourselves, are we using everything that we've got at our disposal? So I think it's important to always be learning and to be sort of self-reflective about how we code, how we debug. It's really useful to find a good mentor and perhaps talk through difficult problems with them. Somebody advised me once, and I've not really stuck to it, to keep a diary of difficult problems I've solved. And I can see that being really useful. You quite often get blog posts where people have described a particularly knotty problem and the steps they took to debug it. And I think that's good advice. And I guess it's important to share stories that we've got. And I'd like to do that in a minute. But before we end, I've got a couple of passages from the book that I'd like to share with you. The first is about determination, hope, and success. It would be a mistake to think that solving problems is an entirely intellectual affair. Determination and emotions play an important role. Lukewarm determination and sleepy consent to do a little something may be enough for a routine problem in the classroom. But to solve a serious scientific problem, willpower is needed that can outlast years of toil and bitter disappointment. Now, I hope none of us have had to debug things that have taken years of toil and bitter disappointments, but it could take weeks. So just having sort of determination and learning how to sort of not get too disaffected is important. So he goes on, determination fluctuates with hope and hopelessness, with satisfaction and disappointment. It is easy to keep on going when we think that the solution is just around the corner, but it is hard to persevere when we do not see any way out of the difficulty. We are elated when our forecasts come true. We are depressed when the way we have followed with some confidence is suddenly blocked and our determination wavers. And he goes on to talk about the importance of small victories. So if you can't solve the immediate problem at hand, if you don't understand the behaviour of the whole system, break things down and just try and understand one piece of the puzzle, and that will make things easier going forwards, I think. And finally, I wanted to read his passage about pedantry and mastery. So, pedantry and mastery are opposite attitudes towards rules. To apply a rule to the letter, rigidly, unquestioningly, in cases where it fits and in cases where it does not fit, is pedantry. Some pedants are poor fools. They never did understand the rule, which they apply quite so conscientiously and so indiscriminately. Some pedants are quite successful. They understood their rule, at least in the beginning, before they became pedants, and chose a good one that fits in many cases and fails only occasionally. To apply a rule with natural ease, with judgment, noticing the cases where it fits, and without ever letting the words of the rule obscure the purpose of the action or the opportunities of the situation, is mastery. The questions and suggestions in this book may be helpful both to problem solvers and to teachers. But first, they must be understood, their proper use must be learned, and learned by trial and error, by failure and success, by experience in applying them. Second, their use should never become pedantic. You should ask no question, make no suggestion, indiscriminately following some rigid habit. Be prepared for various questions and suggestions and use your judgment. You're doing a hard and exciting problem. The step you're going to try next should be prompted by an attentive and open-minded consideration of the problem before you. And if you are inclined to be a pedant and must rely upon some rule, learn this one. Always use your own brains first. Thank you. So if there are any questions, now would be a good time to take them, but also some questions for you. Perhaps you've got some good stories of things that were difficult to debug. Perhaps you'd like to share the techniques or the strategies you used when debugging, or any other ideas or good tools.
So, hello. So this is just an observation about the small victories and the determination and things that that struck a chord with. I think it was a talk yesterday or the day before about TDD, where the whole mechanism of TDD allows you to have small victories and keeps your pecker up, as it were, and you keep going. I have a question as well. You're talking about tools, and I thought at some point you'd mentioned PDB. Perhaps you could talk a little bit about how you use that.
Good point. That's not on my list. It was on my last copy of my list. PDB is a module that comes with Python. It's an interactive Python debugger, and you can set a breakpoint in your code such that when that point is hit, an interactive Python session is launched, and you're able to examine the data in your program at that time. You can move up and down the stack, find out what's been going on, and it's quite useful. But I have seen people who sort of turn to it as their first tool always, and they will basically start at the beginning and sort of hit next, and step through the code line by line, and that can take an entire afternoon to learn what you might learn just by code reading and a bit of common sense. So it's a great tool. I can do a demo later if you want to come and find me, but it's probably not the only tool in your toolbox.
Anybody? Hi, I would like to disagree about the asserts method.
Good.
Really, there's gonna be flame. It was like in early 90s, people would write their library and they will assert some things, like this is gonna be functor or this will behave like this. But that does not give you ability to extend your code. And you should basically move it to the tests, how your stuff behaves, and then somebody wants to reuse your library and change it, like behavior, but he likes your library for some parts. He can write integration test and see what you thought may have his own hypothesis.
Okay, that's a good point. So the point is basically that asserting too much means that users of your code can do less with it. And I suppose there's an analogy here with duck typing. So in Python we have dynamic types. And so you can pass a function, an object, and it's not important what that object is, but it is important how it behaves. So I think it's important not to assert that you get past a widget object. It's more important to assert that the object that you get past has got some data that you depend on, or that is... I guess the most important things to test are that attributes of objects. So the most important thing to assert is that attributes of objects you get are not none, if you're going to depend on those. And your point about testing being the place to check this is good. But in a sort of a complex system with lots of interconnected components, I think it's not always going to be possible to sort of test every interface as thoroughly as you'd like, although perhaps you should.
Well, I also disagree.
Okay, go on.
Because when you have an assert in a complex system, you have to hit whole system and run it to get to this assert, and then try to figure out is this not behaving the way I'm supposed to. But if you don't do it in tests, you can system with their state. And yeah, you can use some libraries for do that. easier, but it's much faster actually.
Sure.
Because you don't have to launch the whole thing.
Sure, but all your code's going to run together at some point, and I think assertions are good for catching where your code doesn't work together as you thought. But yes, you can overuse them, I think.
I think I have some cool story about debugging.
Great.
I learned it from my university. A lecturer told us that he has built a machine, some kind of ATM or registration machine for some hospital. And it took him 1 year to debug it because after kind of 2 weeks, the machine suddenly stopped and froze, and it required a hard reset. So he and his friend started debugging it. One time after such accident, they got their hands on a list of users that were registering, and it appears that the last person was reachable, and they called them, and just suddenly, the friend of my lecturer asked that person if he or she had problems with electrostatic. And it appears that yes, he or she had problems. He couldn't wear watches because he drained the battery in 1 day. He couldn't touch his stereo or pilots. Anything that was bare metal, but was metal, couldn't be used by this person. So yeah, if you debug some software, there are always some strange edge cases you will not foreseen.
Hi. So I'd like to tell a similar story. And happily, I wasn't involved in this because it was rather life-threatening. But it was told to me by one of my lecturers when I was doing my computing degree. And he was talking about, well, how do you test? How do aircraft manufacturers test or tell if a jet engine is on fire, which is obviously not a situation you want to go unnoticed. The problem is that, you know, generally you test if something's on fire if it's hot, but jet engines are already hot. So what do you do? So they figured out, well, actually there's the vibrations of a jet engine running at normal are such and such, whereas if it's on fire, it's likely to be different. So what happens is that when the jet engine has this particular frequency of vibration, a warning appears for the pilot, and in the checklist that the pilot has, they switch the engine off, obviously, because you don't want the damn thing to blow up because it's on fire. But they were actually finding that, and this is a tale of unforeseen consequences here, is that actually pilots were switching off engines that weren't on fire, but the warning light was coming on. It was saying they're on fire, but then when they were looking and there was no flames or anything like that, but you know, there was a checklist. It said you have to switch it off and all sorts. And it took a sort of a bit of a great leap of imagination to actually figure out what it was. And it's all about where you store the fuel in an aeroplane. And you store the fuel in the wings, apparently. And what was happening was that as the fuel was being depleted, the properties of the wings, the weight of the wings, and so on and so forth, because of course the wings are vibrating as well at a particular frequency, and they were interfering with the sensors in the engines. So when you had your gas tank at sort of 3/4 full with this particular aeroplane with these particular weather conditions, the vibrations would be the same as if the jet was on fire, and you got the false warning message. So now they have some way of redistributing fuel so that these things don't happen, I believe. But anyway, I just thought that was an incredible story. Some engineer somewhere deserves sort of a Nobel Prize for, I don't know, lateral thinking, figuring out what the hell that problem was, because it's completely non-obvious. Anyway, that's a fun story about dying on an aircraft.
I've got a friend who designs the the front wing of McLaren's Formula One cars, and he spends sort of weeks in an air tunnel in Spain every year, I guess, doing debugging. But the advantage that we've got over engineers is that we've got a much faster cycle of iteration, so we can have an idea, try it out, and throw it away straight away if we need to.
So I think that most hard bugs to fix are if you have some bad data or bad object and it's passed through the whole system and then system crashes. And the problem is in different part of the system. And this is hard to debug. And asserts help to prevent that, but we have other idea to prevent that than asserts. Like in our company, we have idea that if problem could happen, you should design your code in a way to make the problem happen faster. Like if you want to assert that object is not known, just call a method on it as fast as you can, and you will have exception. If you want to assert that it's integer, you can rather do the arithmetic sooner, and you will have exception. So this works similar to assets, but you don't really need to write assets.
Okay, I guess that's doing the same thing by a different method, isn't it?
Okay, so the question I have is, I think I've heard some kind of a mention of it in a previous talk, but do we have a mechanism to, when we have an unhandled exception, for example in production or something like that, so do we have a tool that can do something like a core dump of a Python process? We can load it later into the interpreter and just step through or whatever?
That's a good question. So in sort of C programs, you can configure the program to dump the entire contents of its memory when it hits an unhandled exception, and then you can load that core dump up into GDB or something and see what was going on at the time. I'm not aware of any tools in Python that offer that, but you could do it. So you can register a hook that will get invoked when an unhandled exception is hit. And I've seen that used to automatically jump into PDB on an exception. I'm sure there will be somewhere somebody has done something to, I guess, create a core dump when that does happen, but I don't know off the top of my head what that is.
Well, I don't think that the dump itself would be a challenge. I think loading it to the interpreter would be a challenge.
Yes. Well, no. So the dump is just going to be Python objects, and you can serialize those or serialize most of those quite easily, I think. Yeah, something to think about anyway.
Thanks.
In Java world, maybe not popular thought, but there is the way of doing this. For instance, if you're running async events, and it's really hard to trace it, debugs because they are on different machines, different threads. If you have event-driven architecture, you can serialize your events and then just replay them. If they are short and well written, you can just basically get all those events and run on your development environment and replay, get the similar thought or similar behavior of the system. Still is for financial systems, so it's, I don't know if it's open source library for it. I hope that there will be.
Perhaps. So I've seen something very similar to what you describe. There's a sort of messaging framework on top of Twisted, and this tool will sort of replay. Well, no, it first captures and then allows you to replay the messages between your actors in Twisted, and that's a useful technique. There's a question or hand up at the back.
There's actually a Python module existing that you can use to basically dump the state of your program to a text file. It's called Python MHA, M-H-A, and it's used by, for example, by the Anaconda project when we have some exception during the run of the installation. There is a window shown up which the user can use to examine the dump and the backtrace, and the backtrace can be submitted to a Bugzilla and stuff like this. So there are some modules for this.
That sounds really useful. Is that open source?
Yes.
Great. Good.
I wanted to ask you whether anybody of you, just raise your hand, spent an hour or more trying to debug a code where you are editing and checking a running version, but the running version was running a completely different code from a different directory. Anybody had that? That means I'm not alone. Okay. So,
well, I have a story like from a battlefield, and that taught me about actually using data when you are debugging. So some years ago, we were working on a new version of the product. We deployed it, and immediately we noticed that, well, maybe 20% of requests are going to hell. It's 500s all over the place. So immediately we rolled back the stuff. We thought for a couple of minutes, what can it be? And we decided, looking at the code, that the code is critically slow because it's using quadratic algorithm instead of linear. So we spent next 2 hours fixing the algorithm and trying to see what is it, with bosses staring at us very angrily because every minute without this feature it's like some money is getting lost. So then we very confidently deployed the second version of this code, and well, 20%, there it is, the 20% of errors, and well, we took a break of 30 minutes just to calm ourselves down and really think about the problem. And someone said, well, how about we use data? And we got into the what we could get from the servers, and it turned out it was just a simple configuration error that some load balancer was configured to load balance to non-existing host, and our firewall was just dropping all the stuff there. So we could have saved 2 hours of work and 2 hours of stress just by looking at data that we actually have.
Yeah, human error is, I think, a big cause of bugs, isn't it? So I've got one story that I'd like to share with you, perhaps before we wrap up and go for lunch. I spent a bit of time working in a small country called Vanuatu in the South Pacific, and I was there doing IT work for the Ministry of Health for the country. It's a tiny country, population about 250,000, and I was the database expert, which was a bit scary. And we were getting problems in that of the 6 provincial hospitals, those in the north could produce reports of their yearly activity, and those in the south could produce reports, but only for the months January, March, October, November, December, and September. And we couldn't work out what was going wrong with the code, and eventually I had to go out to the islands in the south to see what was going on. And it took a very long time before we realized that although the code was the same in the south and in the north, the computers were different. So a bit of a historical background. Vanuatu was colonized by jointly the British and the French around 1900. And the British controlled the northern half and the French controlled the southern half. And so the schools in the north, they learnt English, and the schools in the south, they learnt French. And in the computers in the north, the computer spoke English, and the computers in the south, they were configured to use French. And the person who'd written the code originally had compared the first 3 letters of a month's name against some hard-coded values which happen to be in English. And in English and French, the first 3 letters of a month's name are the same sometimes and different other times. So that took a lot of work to get to the bottom of, and I actually had to go and fly out to a different location to fix. But again, that was human error. So, shall we call it a day there? Good, thank you.